Elettronica Veneta has developed a fuel cell experimental panel specifically designed for educational needs. The aim of the equipment, which includes real professional components available on the market, is performing experiments on the electrochemical energy conversion taking place in a fuel cell stack fed by hydrogen and oxygen. Let us first have a look at the operating principle of a fuel cell system. While hydrogen in pressure feeds the anode of the fuel cell, oxygen present in the air is blown to the cathode by a fan. The electrolyte, a membrane in this case, allows the reactants to combine, producing electricity and releasing heat and water vapor. Notice that the air blown by the fan is also used to cool the stack. Let us now have a look at the main features of the equipment. This is how the workstation looks like. The PEM electrolyzer and the storage tank are needed to feed the fuel cell with hydrogen. This is the control panel that includes all the instruments we need for the experiments. The operating diagram is always at hand for consultation. The hydrogen feeding line includes a solenoid valve, a pressure reducer and a pressure gauge. This is the fuel cell stack, the main element of the system. The load can be adjusted operating this handle. And this is the hydrogen flow meter. Okay, let us switch the system on, operating the main switch, as well as the resistance switch. Now we need to feed the fuel cell stack with hydrogen, connecting the hydrogen storage cylinder and operating its valve. As we may notice from the meter, the fuel cell stack starts operating. We also notice how parameters vary, increasing the load of the system or decreasing it. The manual guides us step by step into a variety of exercises. For example, we can draw the system characteristic curves modifying the electric load applied to the stack and reading several parameters, such as the flow rate and the voltage, current and power output. Elettronica Veneta has developed a photovoltaic panel trainer specifically designed for educational needs. The aim of the equipment, which includes real professional components available in the market, is to perform experiments on a standalone photovoltaic system under different conditions of solar radiation, orientation, inclination, and load. Let us first have a look at how the energy flows during the sunshine hours. The photovoltaic panel converts solar energy into DC electricity. This process is managed by a solar charge controller. The electricity is stored into a buffer battery or converted to feed one or more AC loads. If there's no sun, the energy previously stored in the battery feeds the loads. Let us now have a look at the main features of the equipment. This is how the indoor workstation looks like. And this is the photovoltaic panel. It must be positioned outdoor. It is mounted on wheels, so it is very easy to take outside. A solar radiation sensor is positioned on top. A sun tracking device used to optimize the angle of incidence between the sunlight and the panel is also available as optional. This is how the two photovoltaic modules can be connected to each other, for example in parallel. Here we have the buffer battery. We can just place it on the floor. Okay, let's on the system. First of all, we connect the electric circuit branches using these jumpers. This is the solar charge controller. And here is the inverter. 5 lamps, the AC loads are fixed at the back of the control panel. The manual guides us step by step into a variety of exercises. Let us switch on the inverter. We can see in this area the photovoltaic panel output voltage and current values. Using this selector, we can see the buffer battery input and output voltage and current. And if we switch it again, we can see the inverter input. Elettronica Veneta has developed a solar thermal kit specifically designed for educational needs. The aim of the equipment is to perform experiments on a solar thermal system using a flat plate collector to produce domestic hot water. Let us first have a look at how the water is heated by the solar power. The energy of sunlight is exploited by the flat plate collector to heat a fluid. A pump moves the heat transfer fluid into the collector. Cold tap water is conveyed into a storage tank and it is heated up by the collector hot fluid and then used as domestic hot water. Let us now have a look at the main features of the equipment. This is the main unit, the hot water storage tank, that is best positioned indoor. The operating diagram is always at hand for consultation. These are the different connections, such as the domestic hot water outlet, or the outlet and inlet connection from the flat plate collector, and the tap water inlet. Each connection is monitored by a counter or a meter. This is the sensor to detect the temperature in the storage tank. And this is the outdoor flat plate collector panel. It is mounted on wheels, so it is very easy to take outside. The orientation of the panel can easily be adjusted according to the position of the sun. For better performance, we can also adjust the inclination of the panel according to the height of the sun in the sky. This is the collector temperature sensor. Okay, let us now power the system. The differential temperature controller is working. As we can notice from this counter, the system is now operating. Different meters help us to monitor the temperature and pressure in key points of the circuit. The controller helps us to check the differential temperature between the collector and the tank and their actual temperature. Now, if we let the system work for a while, we can notice how the parameters change. For example, the storage tank water temperature was previously 37 degrees Celsius, but it now increased up to 55 degrees Celsius. And once again, we can take note of how the parameters change looking at this controller. Data collection helps students to exercise on the system performance and optimization. Thanks for watching this video. If you need more information or a quotation, please feel free to contact us. Elettronica Veneta has developed a wind power generator trainer specifically designed for educational needs. The aim of the equipment, which includes real professional components available on the market, is to perform experiments on a standalone wind power generator under different weather conditions. Let us first have a look at how the energy flows when the wind turbine is working. The aerogenerator converts the wind kinetic energy into DC electricity. This process is managed by a charge controller. The electricity is stored into a buffer battery or converted to feed one or more AC loads. If no wind blows, the energy previously stored into the buffer battery feeds the loads. Let us now have a look at the main features of the equipment. This is how the workstation looks like. This is the indoor operation device. An electric motor directly coupled to the aerogenerator shaft simulates the effect of the wind on the generator. Here we have the buffer battery. We can just place it on the floor. The control panel features the operation diagram and includes all the instruments we need for the experiment. Here is the DC-AC inverter. 5 lamps, the AC loads are fixed at the back side of the panel. The manual guides us step by step into a variety of exercises. Okay, let us switch on the system operating these switches.
Let us also switch the inverter on, as well as some of the AC loads. No wind is powering the generator, so the buffer battery is currently feeding the loads. We can see here the wind generator output current, which is presently 0. If we use this selector, we can see the buffer battery current
Veneta
value.
has developed a mini hydroelectric power plant trainer specifically designed for educational needs. The aim of the equipment, which includes real professional components available on the market, is to perform experiments on a real mini hydroelectric power plant under different conditions of water speed, pressure and load. Let us first have a look at the operating principle of the system. The turbine generator unit converts water potential energy into DC electricity. This process is managed by a controller. The electricity is stored into an optional battery or transformed into AC to feed one or more loads. Let us now have a look at the main features of the equipment. This is how the workstation looks like. And this is the mini hydroelectric power plant. The turbine generator unit is positioned on the top. It includes a water distributor. Flow rate and pressure sensors are positioned in key points of the circuit. The variable speed pump simulates the effect of a waterfall. An optional buffer battery unit and a portable rheostat are also available. The manual guides us step by step into a variety of exercises. Okay, let's switch the system on. First of all, we connect the electric circuit branches using these jumpers. The controller turns on. With the current configuration, the AC loads are fed by the buffer battery residual energy. Let us switch the DC-AC inverter on. 5 lamps, the AC loads are fixed at the back of the control panel. Let us now switch some of them on. And notice how the various parameters change accordingly. As we said earlier, the AC loads are fed only by the buffer battery residual energy. Let us now simulate the action of a waterfall on the turbine generator by operating the pump. As we adjust its speed, we check how this action affects different parameters. In this moment, the AC loads are powered by the hydro generator only. Power surplus charges the buffer battery. Once again, we check how parameters change as we switch on the loads. Acting on these jumpers, we now choose to dissipate the power surplus in air. For a comprehensive study of the hydrogenerator performance, the water flow hitting the turbine spoons can be modified acting on some of the jets. Consequently, the height of the water drop increases. This can be noticed observing the hydrogenerator output power. We may also connect an external AC load to the inverter, such as this outdoor spotlight. Again, we check how this action affects different parameters. We can also use a personal computer running Windows for the data supervision. For example, if we switch the loads on or off. We can supervise hydraulic and electric parameters as well as the system efficiency. A very interesting tool allows the student to check the real-time trend of the hydraulic power and electric energy flows. Different colors correspond to different powers of the circuit. Now we connect the equipment to a portable rheostat to draw the hydrogenerator external voltage versus current characteristic curve. Adjusting the rheostat and the pump speed to keep constant the output frequency, we can easily plot the curve and save the acquired data. Which can be of course recovered later. It is also possible to draw the hydrogenerator efficiency versus flow rate curve to find out the point of maximum performance of the turbine generator unit. Again, we can save the acquired data, which can be recovered later. Thanks for watching this video. If you need more information or a quotation, please feel free to contact us.